We're going to move right along to our next session with a little bit of furniture rearranging here. Okay. All right. Up next, we have From Archive to Action, Reimagining AI Video Pipelines with Archival or Hierarchical Codecs. And this is presented by Guendalina Cobianchi and Andy Beach. Guendalina is a Senior Vice President of Strategic Analytics and Business Insights at VNova, a specialist in data compression. And she has contributed to the development and promotion of hierarchical data formats like MPEG-5 Part 2, LCE VC, and SMPTE VC6. Andy Beach is a media and AI strategist working at the intersection of storytelling, technology, and innovation. Formerly the CTO for media entertainment at Microsoft, Andy now advises a range of companies focused on Gen AI, cloud-native production, and immersive media platforms. Come on up.
Hi, everybody. Thank you so much for coming to the talk. Really appreciate it. We also have Brent Yates in the audience from Switch.io, which was a key part of both the paper and the demo that we're going to look at. We are focused in this one. We originally started off with a little bit more around both live and archival work. But for this, we really focused on the live workflow because we saw such benefits, and it was really an entire paper by itself. So very quickly, just any additional pieces, Gwenda, on your?
No, VNova is a video compression specialist company, and more recently, I've been focusing in developing the exciting new AI applications based on our hierarchical codec. So here you'll see an example.
So in my time at Microsoft, one of the things that I'd spent a lot of time with was relationship making. I would find companies that had interesting technologies, but they needed to come together to make a solution. And this was me sort of still doing my old job after I left Microsoft, because VNova came to me originally with VC6 to talk about the AI capabilities of the codec. And I recognized pretty quickly that there was a ton of value in bringing it into a live production workflow. So that's really the focus that we're going to talk about. One of the things that we saw in that work was how the shift in AI really makes for a bottleneck in the architectural reviews that we're talking about. And by that, what I really mean is that when you're using the traditional mezzanine codecs today and moving it into the cloud, the reality is that in order to leverage an AI workflow, you're typically having to do full frame decodes or potentially even multiple renditions of the content as proxies to get it to the various models that are needed. So that's relatively inefficient. You're just starting to add additional architecture to what's going on. B, you're also creating a lot of extra compute and storage needs that are in there. And then you're also building latency into it, which is always the death for anything that's in a live workflow, obviously. So if we look at what VC6 does combined with Switch.io, what we really have is an industry compliant, compute native hierarchical format that allows for selective decode and region aware fetch of specific parts of the content as it comes through. And then we're coupling that with a ground to cloud intelligent multicast network. That ends up with what effectively is an AI native live workflow that allows for a single VC6 mezzanine stream to serve out multiple models without any kind of redundant encoding or proxy work to be done as part of the process. So, Gwenda, could you explain a little bit around the format?
Yes, of course, Andy. Thank you for the introduction. So, VC6 is a compute-aware hierarchical codec that has been standardized in SMPTE as ST2117-1. And differently from other codecs, VC6 represent the image as a ladder of different video resolutions. So you can imagine it as a pyramid, a reverse pyramid in this case, where at the lower level of the pyramid, you can do a very quick high-level look at the big picture and see what's going on in the scene. And the more you move up in the pyramid, you have gradually more and more details available for further analysis and for more detailed recognition, for instance, of certain details. So this format basically allows three key things that were hard to achieve with the traditional codec. First of all, you have a fully hierarchical sequences on frame, and you can read any level of quality that is suitable for, specifically in AI use case, for a specific AI model. You can run player tracking on a football match at a very low level, but if you want to recognize the player or read the number in the jersey, you would need a maximum level of quality. Actually, this is a good example. Think about an Ultra HD football match. Of course, at 4K quality, you have every detail you may need across the full frame, but it's also quite heavy. We're talking about 2 megabytes per frame. If you're running an AI model, you don't need 4K resolution to track the players. We have an example of a 540p, which would be 2 levels of quality below the original 4K frame, which means 75% lower bitrate, but an AI model would equally be able to track the player with the same accuracy that you would have with a 4K, but you're saving a lot of data and a lot of I/O and processing with the model. But you can go further down. This is an example where you go down one further level in the pyramid. We're talking about a 270p at 10 times lower rate. Of course, the image is a little bit blurry, but you can still track the player. So this is a perfect example where you can feed directly the bottom layer of the pyramid into the AI model in a very, very effective way. But then let's say that you want to track a player because you want to personalize the feed and you have a fan base of this player number 22, and you want to make sure that you can read the jersey number and recognize potentially the face of the player. In that case, you need the maximum level of quality and resolution that the 4K feed would allow you to have, but you don't care about the rest of the frame. You just care about that specific region of interest, but we may be talking about less than 1% of the pixels. So you can see if you only fetch and transfer that little portion of the screen, you save quite a lot of data and data egress and I/O and processing, etc. So, summarize the key features of the SMPTE VC6 standard as opposed to other image and video mezzanine standards. Of course, JPEG is ubiquitous, is extremely fast, is everywhere, but it's kind of a basic codec for image representation, and it cannot do many things. So there's no concept of the hierarchy, and it goes up to 8-bit. But of course, ubiquitous and very fast. If we move to other mezzanine codec more advanced, like JPEG 2000 or even the more recent JPEG XS, we're starting to have more hierarchical features and different layer representation. However, they still have some limitation due to the wavelet transform that are at the base of the codec. And so you cannot yet be very precise in decoding exclusively the part of the screen that you would want to give to the AI model. And even more importantly, you still need to download the whole file, the whole frame, and then process it in order to extract what you need for AI. This is exactly the issue that VC6 is solving, because in addition to the capabilities of doing lossless, high bit depth, and all the hierarchical feature of the other codec, it also allows you to really fetch and recall only the data that you care. So it's very, very efficient to enable AI models.
Very good. Thank you for that. So what does this look like if we implement it into a real world scenario? Effectively, what you'd be looking at then is a ground instance, some on-prem environment where you've got ideally 2110 coming in to Switch IO, their ground switch product that has VC6 implemented, where it would turn it into a mezzanine signal to head to the cloud. If, however, you're working in an SDI environment, you can actually also use NVIDIA's Holoscan for Media solution, which has both ground switch and VC6 as plug-in options within it. So that allows you to either go SDI or 2110 into a VC6 environment that gets you to the cloud. Once it's in the cloud, we're using And in this implementation, we're using Azure, although I'd like to point out that it's also cloud agnostic. It works in Amazon as well. It works in OCI, works in Google. There is no cloud that this won't be implementable in. But for the purposes of this, we're going into Azure with it, and we're using Cloud Switch to then fan that out to multiple models. And again, because of the flexibility that BC6 gives us, we're able to put the specific image or the specific region of the image that the model needs into it without any reduction in latency, without any additional hits on compute or other pieces that are going in. Another piece that's valuable here that Switch has been working on is the agentic workflow. So they're creating a series of agents to orchestrate the feeds that are going in to help you effectively pick the right models that you're doing. So you'll have the ability to not only go physically assign a model to a given series, you can ask an agent to help you find a detection model or to find something that'll look for slates or color bars or other pieces that are part of it. And it can actually bring up multiple models simultaneously to allow you to find the one that's best for the solution of the need that you have as part of it. So there's a lot of thought that's been gone into how to make this sort of as easy as possible to bring an AI process to a live video piece without adding a lot of different parts of the solution to the human operator's workflow.
So let's look at some numbers to see in practice how the BC6 integration within Switch works. So I'm starting from some lab tests that we've done in collaboration with NVIDIA, testing the BC6 decoding performance against other codecs on NVIDIA GPUs. And first of all, we tested BC6 decoding across the different implementations, CPU and GPU with OpenCL and with CUDA. And as you can see, the GPU implementation is incredibly efficient, and we're talking about roughly 1 millisecond per frame decode time. So it's very, very fast. And the speed actually becomes, in theory, should scale with the resolution. As you can see, is not yet the case. There is still some CUDA optimization ongoing with the NVIDIA DevTech team, but we are very confident that we're going to go sub-millisecond, even for large frames. Actually, if you scan the QR code, there is an interesting developer blog that we published about a month ago with NVIDIA. Comparing to other codecs, we are running a number of experiments to see how fast is BC6 as opposed to other, even GPU-optimized implementations such as NVIDIA and the image codec. As you can see, it's actually even more efficient than NVJPEG in CUDA, and it's an order of magnitude more efficient than JPEG 2000. So it's indeed massively parallel and very suitable for GPUs and very, very fast. If we then move to the real-life implementation within the live multicast workflow on the Switch network. In terms of network efficiency, of course, we compare against ST2110. And in terms of bandwidth, we're talking about an order of magnitude saving for a quality that is not lossless in this case. BC6 can also do lossless, but it's a very good mezzanine quality that does not affect the accuracy of the AI model. So in this case is over an order of magnitude saving, which can be very, very handy in transferring the data, for instance, from the ground switch to the cloud, and potentially we can also do it losslessly and then convert back to ST2110 if it's needed. In terms of performance and timing instead, BC6 is very, very fast. So if you decode BC6, the top layer of quality is roughly half the millisecond of decoding ST2110, and the benefit goes further down if you decode a lower resolution in order to feed the model directly with the resolution that is closer to the model, to the resolution that is required by the model. So we're talking about a 70% saving in decode time, which is then converted into a reduction in latency, as we will see. In terms of transmission, so you may ask, what is the impact of basically adding the step of transcoding to BC6? Actually, as you can see here, it basically comes for free because managing the packets of ST2110 is actually quite expensive. So the transcoding to VS6 actually doesn't add any further latency. Actually, it's the other way around. The 30 milliseconds that you see here was done on the CPU. We are now integrating the CUDA encoder in GPU, and we expect to actually shave down this number by a pretty big amount. And at the end of the story, the impact on latency is actually pretty good because you can have a full end-to-end system with the same accuracy that you would have with the ST2110, but with like a third of the latency. We're talking about 300 milliseconds end-to-end.
Very good. So overall, where does that leave us in terms of the strategic implications? Sorry. Ultimately, it comes down to operational efficiency. I mean, part of the goal of this was to just make for a more efficient architecture and pipeline for getting content into the cloud, where other processes were going to occur, particularly AI, but presumably other pieces as well. Also, the need to reduce bandwidth and cloud egress charges that might be applicable that go on there. Some of the nice pieces that came along with it, though, were scalability. Just being able to use multicast as a fan out to the other models makes it highly efficient to bring other new AI models and workloads into it. So I don't need to go build new pipelines effectively every time I want to add or test a new model as part of it. I can almost pick it as if I'm choosing from a catalog or a library as part of a broader workflow. And then there's sustainability pieces that have come along with it as well. We're obviously lowering the compute load, which is reducing the overall power consumption per channel that we're able to achieve. And we're also reducing network traffic, which lowers the overall energy footprint as part of that. So these are just some of the early use cases that we've been exploring with it. Obviously, intelligent video analytics is sort of a big piece of that. Think of things that you can automate, particularly around like a distribution ops pipeline or a broadcast ops pipeline as part of that, where you have lots of eyes on glass, but you can't have them on every single piece of glass all of the time. You can automate a lot of the pieces, looking for dropped frames, looking for missing audio channels, other pieces of the solution. Likewise, there's a lot of data that can be gathered from the frames and the signal as it's passing through the system that can be passed on to production units and other pieces as part of that broader piece. And then I think this dynamic replay and highlight generation becomes a pretty critical part of it. Being able to analyze this thing, each signal as it comes in at this level of detail will allow for very fast turnaround on things like VAR solutions in the future, which are all looking for ways to move into the cloud. And today they just haven't been able to achieve it because of resolution and latency limitations. And then I think the early work switch is put in around the agentic network controls and making this interoperable with other agent orchestration systems will be critical so that you don't have an island within the production workflow that exists, but you have something that knows how to talk on a standards basis with other MCP units. And so I think if we can leave you with anything, really the key takeaways are starting with SMPTE-VC6, having a hierarchical region-aware format allows us to sort of change the latency and cost perspective on live AI pre-processing that needs to be done. Coupling that with intelligent multicast enables for those workloads to be shared across a single source rather than trying to spin up multiple sources to do it. And overall, it sort of combined together leaves us with a standards-based scalable foundation for how we think about AI in live production scenarios as we move forward. So thank you very much for the time. Hopefully you guys have a couple of questions that have come in.
That was great. Thank you.
Thank you.
Right. Yeah, we have a few questions. And as a reminder, if you have questions, there are QR codes around the room, or I might end up calling on people. So one question we got was, what kind of additional standards work needs to happen for optimal agentic network control, if any?
So that's a great question. It's more around the data more than anything, how data gets organized so that systems can easily share it back and forth is probably the primary work that's going on. I know that the AI working group that SMPTE has is looking at some of those data standards now and looking to start informing and making decisions and recommendations as we move forward.
How does VC6 compare with high throughput JPEG 2000?
This is another very good question. I guess the question is in terms of quality and processing potentially. So in terms of quality, VC6 is a mezzanine format, is an intra codec, so in a way similar to JPEG 2000. We're still running a significant visual quality test at scale, but we run tests against traditional JPEG 2000, and we're roughly the same ballpark, and in many cases, like 10-20% more efficient. JPEG high throughput is slightly less efficient from the visual quality perspective. I think roughly in the order of 7-8%, but is incredibly much faster, especially with the NVIDIA implementation in GPU. We noticed that it was almost an order of magnitude faster decoding compared to JPEG 2000. We're still slightly faster, but basically it's closer to the performance of VC6. In any case, we are also working and collaborating with the NVIDIA and the image codec team and the DevTech team to further optimize the code implementation and make it as efficient as possible.
Great. Thank you. When you talk about reduction of cloud egress charges, what kind of order of magnitude might that be? I guess, what are we talking about in terms of real dollars?
I mean, how long is a piece of string is sort of the answer here, unfortunately, because it really depends on the individual workflows and how much you're already outputting. I know that, we talked about some scenarios with commercial productions where an individual event might involve bringing in 26 different channels simultaneously, and they're still outputting multiple channels, although obviously not that many. So the question starts becoming, how much AI are you adding to your workflow? How many reductions can I bring into the cloud that allow me to output or move less signal around as part of the process? So I think it's going to be, unfortunately, an individual answer for the production. We all do production differently at the end of the day, and it's going to change that.
But it depends also on the AI use case. So
That's
in
fair
general, every AI use case that has to do with analyzing only a specific portion of the image. The example that I showed you earlier about a football player, this is where you may have a significant reduction in egress, because if you only have to move that specific bit of the image without having to do all the scaling and cropping that you would have to do normally, that could be even like 2 order of magnitudes compared to moving the full frame. So again, it depends is the answer.
Great. This question kind of got cut off, but I think I know where they're going. Codecs like ProRes, DNX can retrieve, decode lower res renditions for efficiency, building renditions for the preview or multicast window. Is this similar or the same as, and that gets cut off, but I think if they meant EC6 and so on.
So I'll let Gwenda answer most of this, but I'll say the scalable video ladder notion as part of this, certainly gives you the ability to pull instantly out effectively a lower resolution as part of it. I think the additional bonus of that region of interest, being able to identify a bounding box in just specific parts of the frame that you pull out, is something that I've not seen any other standard out there able to do, or non-compliant codecs able to do as part of it.
No, absolutely. And also compared to ProRes, for instance, if you have if you want to monitor several different video feeds, and you typically would have a mosaic with, 9 feeds on the same screen, you can actually decode simultaneously 9 VC6 videos at maybe 2 levels of quality below the full resolution. And then the moment you click on one that is the one that you care about, you can pull up the full resolution for that and actually forget about the other. So it also gives you the flexibility to navigate in absolutely real time on a frame by frame basis, the level of resolution that you want to pull. So there's actually a very good use case for that purpose as well.
And what are the royalty considerations around using VC6?
So a lot of the licensing is still being determined at this point.
Thank you for saving me, Andy.
We are actively working with Vinova to find something that's the right balance, for how it is going to be moving forward. And actually those that are interested in trying it, we're eagerly taking advice on what works best for them as part of it. So open to suggestion.
Absolutely, but it will be very transparent and well communicated in advance. I mean, you might be familiar with other Vinova Codec and PEC 5 LCC. We always tend to publish the licensing terms up front in a very clear way so that there is no uncertainty. And the idea is that the business case must always be absolutely worth it. So
yeah. And on the Switch side, it's a relatively inexpensive service to bring online. It's sort of cents per hour of use, for using that network overlay and transfer. So all in all, it should be a relatively, inexpensive solution to try and implement.
And can VC6, reads be limited by bit depth? So if you only need half bandwidth memory for 8-bit out of a 16-bit file.
Sorry, I didn't get
the bit depth.
The bit depth is up to the standard support up to 30.
Can it be halved is the question. Like, could you return like a 16-bit out of a 31-bit piece? Or we were talking about color depth earlier as well. And
Yes.
I did forget to mention that as part of it. So you might want to speak to that.
Yeah, actually, you may be answering that question better than me.
Sure. So the answer is yes. Today you can return, different bit depths as part of it. You can also return strictly different color space as part of the either the region of interest or the frame, LOQ that you're asking for.
Thank you, Andy.
No problem.
And what is the performance difference between VC6 and DNX or ProRes for decoding?
So have we tested against DNX?
No,
Okay.
not yet. So noted, and it will be done.
Yeah, as we move more into the archival space, which is sort of the next task, we'll get more into both ProRes and DNX comparisons.
We have time for maybe 1-2 more questions if there are any. If not, hang on, let me come to you, Wendy. Where does 31-bit depth come from?
It's from the standard specifications.
Yeah, it's part of the standard spec. I don't know why the extra bit was reserved, if I'm honest, because I haven't read the spec that deeply. But it's inherited directly from the SMPTE standard.
Because there's one bit that serves for sign, I think.
Oh, for signing it?
Yeah.
Got it.
Yep. Okay. And maybe one more question if there are any. This was a very thorough presentation, so that's okay.
Thank you for playing Phil Donahue.
All right. Let me check our questions. It doesn't work when I have a microphone in front of my face. All right. That's it. Well, thank you all so much. This was a great presentation and I appreciate it.
Yeah.
Thank you.
Thank you.
Thank you.
Thank you.